Yeah. Thank you very much, and thank you to the organizers for giving me the opportunity to share with you some of the recent work we have been doing. So what I'll be talking about today is about quantum classical transition in spin systems that are strongly coupled to an environment. And in this talk, I will touch in a bit more detail some of the points that Janet Anders mentioned earlier today. So one of the fundamental key questions of thermodynamics is, of course, understanding what is the steady state of a system, to what state a system equilibrates. So we have sorry. Okay, it's a bit, okay. Okay, now, sorry. So we have a system that's interacting with an environment, okay, at a given temperature. And as we let the system interact with the environment, it eventually thermalizes and reaches steady state, equilibrium state, right? So we look at the dynamics, the system is going to evolve in time and reach a steady state. And the question is, what is the steady state? What is the equilibrium state that is reached, right? As it's a very well-known result of a system that is weakly coupled to the environment. The steady state is given by the Gibbs state, which is just the exponential minus the Hamiltonian of the system divided by kT, right? This is a very well-known result, nothing surprising here. Now, what is much more interesting is asking ourselves, what is the equilibrium state? What is the steady state when the interaction with the environment is non-negligible, right? In principle, it can be very strong, but even if it's not super strong, but at least strong enough to induce some corrections, and we cannot just ignore it. Then whether the steady state is the Gibbs state enters into question. And in fact, it is known, many particular examples that one can look at, the equilibrium state then is not the Gibbs state, and one needs to introduce some corrections to it. In general, proving what is that equilibrium state is hard, and there is no known solution valid at all coupling strength. One approach to finding this equilibrium state, it was known as the mean force Gibbs state, right? Which postulates that the equilibrium state is given by the thermal state of the whole Hamiltonian, so the Hamiltonian system plus environment plus interaction, and then tracing over the environment. This is a very reasonable assumption because all it's saying is that the environment, all it's doing is just equilibrium everything at a given temperature, but the state of the system, one needs to take into account the interaction, so it's not just the Gibbs state, but one needs to take the whole Hamiltonian, the thermal state of that, and then trace the environment. Although it's a very intuitive assumption to make, it has its complications from the practical point of view because computing that trace can be very hard. And also the reality is that it is not really proven at all coupling strengths whether the dynamical steady state is actually given by this state. It is known in some particular limits, like the ultra-strong limit, in the weak coupling limit, this has been proven, but for arbitrary couplings, it's not been proven and remains an open question. Now, strong coupling thermodynamics have been studied for many years now, both in the classical and yes.
I mean, you were trying to talk on Friday, so it makes sense for you to have that again, but now
But yeah, so a lot has been said about strong coupling in quantum and classical systems, right? But the reality is that although a lot has been studied, there is few works where they look at what is the relationship between two different regimes, how one can transition from the quantum to the classical regime in systems that are strongly coupled to an environment, right? And this is an interesting question for several reasons. In particular, one might ask yourself, what parameters control the quantum to classical transition in a system, right? So what parameters of the system are going to make the system behave more classically? Now, this is interesting because understanding which parameters control this transition allows us to understand under which conditions a quantum system can be well approximated by the classical one. And finally, this is also interesting because normally computing properties of a classical system is much simpler than of a quantum one. So, for example, in the example that Janet mentioned earlier today of these magnetism systems, one can be interested to understand what kind of quantum correction one could add to the classical simulations, understand when one needs to add corrections or not. So, understanding which parameters control this transition can be very insightful. So, since I will try to do quite of a quantitative analysis of these questions, I will look at a specific model. And the model I'll be looking at is a spin of arbitrary length that is coupled to a bosonic bath. So the total Hamiltonian of the system is the system of the Hamiltonian of the system, which is just a spin with it has some energy basis I choose arbitrarily in the direction. Then there is an environment which is just harmonic oscillators, it's a bosonic bath, and then we have an interaction that is bilinear between the spin and the position operators of the bath. And the interaction with the spin is in principle in some direction that is not the same direction of the bare Hamiltonian of the system. So this Hamiltonian works both for the quantum and classical case. In the quantum case, the spin operators are going to satisfy the standard quantum commutation relations of spin operators, and the classical case is just going to be a vector of a given length. And this can be used to model many systems like spins in magnetic field, but basically any discrete level system, quantum discrete level system, can sort of be mapped into this kind of Hamiltonian. So the application is varied. So let me first focus for a second in the classical case. Okay, for the classical case in particular, that mean force state can actually be computed analytically at arbitrary coupling. And in fact, one can compute that trace of the environment analytically, and what one gets is this expression here. So the mean force state look like this: is the thermal state of the bare Hamiltonian Hs plus an additional correction, which is squared in the interaction spin operator with the environment, spin variable with the environment. Okay, and this Q that appears here multiplying the correction is what's called the reorganization energy, which is just an integral over the coupling strength with the environment, the coupling operators, the coupling function with the environment. Now, this can be computed analytically. So we have, for the classical case, we have the mean force with state are arbitrary coupling strength. Now we can ask ourselves what's happening with the dynamics. Do they actually converge to this state or not, right? As also Janet briefly mentioned before, in this work here, it's been shown that for particular coupling functions with the environment, Lorentzian in particular, one can find efficient numerical methods to solve the dynamics at arbitrary coupling of this classical spin. And we have implemented this. It's publicly available for people to use, and one can therefore simulate this arbitrary strength coupling to the environment, the whole dynamics of the classical spin. So how does this look like? So what I plot here on the left is the exploitation value of the z component of the spin, on the right of the x component as a function of temperature. Each dot corresponds to the steady state of the spin, right, at a given temperature and at a given coupling strength. So each color corresponds to different coupling strength. The lighter the color, the stronger the coupling. So this is the steady state from the dynamics that we solve numerically. And then we can compare that with this analytical formula for the mean force state, and that's the solid line, right? And as you can see, there is an excellent agreement between the two. It's worth noting that the values of these coupling strengths that were chosen here are not arbitrary, but they cover the whole range, as we will see towards the end, from very weak coupling to very strong coupling. So basically, and we have done it for more curves than this one that we show here. So basically, numerically, we can show for this system in the classical case that really indeed the dynamics converge to the mean force state at arbitrary coupling. So this is a numerical proof, but it's a numerical evidence that indeed this state well describes the equilibrium state of the system's coupled non-trivial to the environment. Okay, so now let me move to this other question that I mentioned in introduction about the quantum classical correspondence, right? So we have a spin. If I ask in which case the quantum spin resembles a classical one, the obvious answer is when the spin length goes to infinity, right? Because then the energy levels, the spacing decreases between energy levels, and it resembles more like a classical vector, right? That's the intuitive idea. Now, if we look at the Gibbs state, the standard Gibbs state, even then there is a bit of an issue, because if one just takes naively the limit of the spin going to zero, one ends up with a trivial limit that doesn't really say anything. So to actually get the classical statistics from the quantum one in the case of the large spin, one needs to do something a bit more delicate, which is, for example, introduce a temperature rescaling of this kind, right? Where one says that the temperature, well, the spin length divided by the temperature remains constant as the spin length increases. If one does that, then it has been proven before. There is this result by Miller, Leff, and Lieb, where they show that then the quantum partition function converges to the classical one, right? But one needs to introduce this scaling in the temperature. Now, what happens if we go beyond the very weak coupling where everything is described by the Gibbs state and now introduce this environment in these corrections? Then we have the classical mean force Gibbs state. Let's look at for a second at the classical mean force Gibbs state. It looks like this. And if you look at it, there is this subtlety that the interaction term, right, scales as the spin length square, while the bare Hamiltonian term scales as the spin length, which means that if we just take the limit of the spin going to infinity, the interaction energy is going to grow much faster than the bare energies of the system. So again, we are going to end up in kind of a trivial limit if you just take the length of the spin to infinity. So one again needs to do something more delicate. And what one needs to do, for example, is introduce scaling the coupling strength and say that the coupling strength goes like 1 over the spin length, right? And this scaling together with the temperature scaling as before has the property of leaving the mean force, classical mean force state invariant. And this is needed to get a well-defined limit that is just not a trivial one. So we have this temperature rescaling, we have this interaction rescaling. Both they live in both the classical mean force state and the classical dynamics invariant. then what we can prove analytically is that the quantum partition function converges to the classical one at arbitrary coupling. Even though we don't know analytically what's the expression of the quantum partition function because we don't know it at arbitrary coupling, even so we can prove the limit. Okay, I won't go into details of the limit because they are extremely technical and won't say much. So let's instead look at what this looks like in terms of plots, right? So what I plot here on the right, on the top, the z component of the spin, on the bottom, the x component of the spin as a function of temperature. This dashed black line is the classical mean force prediction, okay? Now, this purple line is the quantum mean force prediction for a spin length of 1/2, okay? They clearly are quite different. Now, this lighter, darker blue one is, is for a spin length of 2/2, so spin length 1. As you see, is getting a bit closer to the classical one, then 5/2, getting closer, and an extreme case of 1,000 halves, so spin length 500, is the light green one, and has perfectly converged to the classical mean force prediction. Okay. Again, we can prove this analytically for arbitrary coupling. This is just a qualitative example to show you how, as the spin length increases, we have this convergence to the classical limit. But introducing these scalings both in temperature and coupling strength. This is important because under these circumstances is where the classical limit does work in terms of getting the classical partition function. If any of these scalings in a real situation doesn't hold, then the limit is going to be different. It's not just going to be the classical prediction. So if you look at this plot, there is something interesting that one might notice is that if you look at the x expectation values, they're different from 0. And I remind you, the Hamiltonian of the system is proportional to Sz. So in all the quantum spins that we're plotting here, this means that in the equilibrium state, there are coherences in the energy basis, right? Which is something very peculiar. And it has been noted before. There is, for example, this paper by Burkayasta and others where they show that there are environment-induced coherences if one goes beyond the weak coupling limit. For a quantum dot they look at in this case. But the point is, in all these cases, there are coherences in the steady state, right? Now, what's interesting, more interesting is that if you look at the black dashed line, which is the classical mean force prediction, there is also an Sx different from 0, okay? So, and it's even larger can be even larger than the quantum one. Now, this is interesting because what this is telling us is that the fact that this expectation value of X is different from 0 is not entirely a quantum effect. Like it sometimes has been pointed as a quantum effect, and while indeed it means that there are coherences because I mean in the energy basis, if one has X different from 0, there is quantum coherences, but the origin of this effect is not a purely quantum one, but instead it has a much simpler explanation if you want to. And what we argue is that this is due to a particular coupling interaction that one is choosing that has certain anisotropy with respect to the coordinate system one is choosing. So the coupling strength is the coupling term is such that it induces an anisotropy, and this anisotropy produces this expectation value of X different from 0, and this is true both in the classical and the quantum case. So seeing this as X different from 0 in a particular case is not an immediate evidence of the quantum nature of the system, but is just evidence of a particular interaction with the environment. It's not a purely quantum effect, but it has also a clear counterpart in the classical case. And this is also quite interesting because I won't go into the details of this. If anyone has questions, I could go later in the question section, but there are some recent works by Janszycki and others where they argue that for many quantum thermodynamic processes that have been studied and protocols, there is a classical analog where the quantum coherence is replaced by some kind of homogeneous probability distributions over the energy shells of the classical system. Again, if anyone has questions, I'll go into the details, but there is they propose this kind of correspondence between quantum thermodynamics extracting work from coherences or doing stuff with coherences and classical systems with these inhomogeneous probability distributions. And this is exactly what's happening also for us here. This classical mean force state we can see has these inhomogeneous distributions over energy shells. So again, it seems that indeed this correspondence seems to be quite strong, and it's quite interesting that some things that have been attributed to quantum coherences have a very clear classical counterpart. To move toward the end of the talk, I will go a bit about different coupling regimes. Okay, this is also something that Janet went a bit earlier, so I'll go quickly over it. But if we have a system, right, we have the system Hamiltonian, the environment Hamiltonian, we have the interaction. As one increases the interaction, one can explore a lot of different regimes, right? When the interaction goes to 0, we have this ultra-weak limit where the statistics are well described by the Gibbs state. As one increases the interaction rate, one enters a weak coupling regime where a second order expansion is well described the system. Then has an intermediate regime, which is the complicated and most interesting one, and in the limit of the interaction going to infinity, one gets into the ultrasound limit, right? Now, what's going to be interesting for what I'll explain in a second is that both in the weak coupling and the ultrasound limit, we have analytical expressions for the quantum mean force state. Okay, the classical one we have solved for coupling strength, but the quantum one only has an analytical expression for the weak coupling and the ultrasound coupling. In the intermediate coupling, we don't really have an analytical solution, and it can be, in principle, quite hard to compute. So, what do these coupling regimes look like for our specific system? So here we'll focus in a quantum spin-1/2, right? So what I plot here at the top is the z expectation value, on the bottom the x expectation value as a function of the coupling strength of the lambda. Okay. So and this is all at temperature 0 for now. So I'm fixing the temperature at 0 for the environment. So this gray line that I'm plotting is the Gibbs space prediction, right? Which doesn't depend on coupling strength because in fact it's the limit of the coupling going to 0, right? So the x is 0 and the z is 1. Pretty simple in this case. Now, if we start turning on the interaction, we have to go into the weak coupling regime, and then we have to introduce the corrections of the mean force Gibbs state, which have an analytical expression for weak coupling, and this is the dash blue curve, right? As a function of coupling strength. As you can see, we can identify here a region where very clearly the blue line and the gray line are almost identical, right? And this is the ultra weak limit, where again the statistics of the system are well described by the Gibbs state. But as we in Gibbs structure state, there are clear discrepancies between the two, which means we are moving away from the ultra weak limit and moving into weak limit, where we have to introduce these corrections. Okay. Now, the other case where we have an analytical expression of the Gibbs mean force Gibbs state is the ultrasound limit, where the coupling strength goes to infinity. Again, this is the in this case the green line, and this again doesn't depend on coupling strength because again it's a limit of coupling strength going to infinity. So to understand where the weak stops being good and one starts having a good approximation by the ultrasound, we need the intermediate regime, which analytically we don't have. So we solve numerically for this particular system and for some particular kind of couplings with the environment using the direction coordinate mapping. One can numerically treat this problem, and this is the solid green line. Yeah. So what we have here is this. The solid green line is this quantum mean force state numerically solved. So we can see here a region where the solid green line matches very well the dashed green line. That means that ultrasound limit is valid there, and whatever is in between is the weak limit. Sorry, the intermediate limit, where it's the one that's very hard to analytically treat. So all of this has been at temperature 0, but one can do the same analysis for finite temperature. So what I plot here is, as a function of temperature on the vertical axis, coupling strength on the horizontal axis, for given combination of temperature and coupling strength, which of these approximation of these regimes is valid, where the ultra weak limit is valid, where the weak one, where the intermediate, or the ultra strong. As you can see, as the temperature increases, the boundaries shift towards higher coupling strength, right? What this means is that at higher temperatures, it's easier to fulfill the weaker limit approximations, right? In particular, for example, at this coupling strength, right? At this temperature, we go from weak to ultra weak limit. At this, we look at the intermediate, this temperature we're going to the weak. If we keep increasing the temperature, eventually the ultra weak. So what is to be strongly or weakly coupled to the environment depends very strongly on the temperature of the environment, okay? That's the take-home message from this plot. And then finally, on this end, like this was for the quantum spin-1/2, right? Have this plot. One can do the exact same analysis for the classical one, exactly the same. And this is what one gets. This is the quantum one, and this is the classical one. Okay, so the quantum and the classical. Qualitatively, they look very different. Very similar. But there is one key difference, which is that the boundaries of where each region is shifts a bit towards weaker coupling for the classical one. So if you look at the classical, there is this dot here, right, which is given coupling strength. For the classical one, here we have intermediate coupling, while for the quantum one, here we have weak coupling. So it means that whether something is also weak or strong coupling depends also on the nature of the system, whether it's quantum or classical. Okay, so with this I finish. So in conclusion, after showing you, we have this closed analytical expression from the classical mean force state at all couplings. We have numerically verified the conversion of the dynamics to this classical mean force state. We have looked at this quantum classical transition where we can prove analytically that the quantum state converges to the classical one at all couplings, given these particular scalings on the interaction and temperature. and we are giving this thorough characterization of the different coupling strength regimes, which again gives a clear idea what one means with strong, weak coupling, which sometimes in thermodynamics is used very vaguely and unclearly, and here we have a good characterization for this particular problem. So I thank all of the collaborations, my collaborators, and I thank you for listening.
Thank you very much, Federico.